An introduction to differential equations. In this session, we will go through certain prerequisites that will aid us in solving differential equations. These ideas come from calculus. It is necessary for the learner to have a thorough grasp of the tools in order to have a better understanding of the techniques of solving differential equations. 1.1. Integral of a function. An important ingredient of differential equations is integrals. The knowledge of various techniques of integration helps in solving tricky differential equations with ease. We will discuss few of the useful methods of integration. Definition: the integral of a function f of x with respect to x, denoted by integration f of x dx, is defined as a function g of x such that differentiation of g of x gives f of x. Thus, integral f of x dx is equals to g of x, which also implies that g prime of x is equals to f of x. The function g of x is called an integral of fx. Note: if g of x is an integral of function f of x, then g of x plus c is also an integral of f of x, where c is an arbitrary constant, since derivative of g of x plus c is equals to derivative of g of x plus 0. Because derivative of a constant is 0, that gives us g prime of x, which is also equivalent to f of x. C is called the constant of integration. Illustration. Number 1. Integration of the function x cubed with respect to x gives us 1/4 of x raised to the power of 4 plus c. That is because if we differentiate 1/4 of x raised to the power of 4 plus c, we get x cubed. Number 2. Integration of cosine dx gives us sin x plus c. That is because when we differentiate sin x plus c, we get cosine of x. And lastly, integration of e raised to the power of x dx, which is the exponential function, gives us e raised to the power of x plus c, and that is because differentiating e raised to the power of x plus c gives back the integrand e raised to the power of x. The following table lists out some of the standard formula of integration. Go through the description box to download the PDF version of this particular formula. 1.3. Methods of integration. Following methods are used frequently to solve certain differential equations. Number 1. Integration by substitution. Let us consider an example. Number 1. We have integration of the function tan inverse of x divided by 1 plus x squared. So we have to integrate it with respect to x. Now, this is being an integration by substitution method. We are going to substitute tan inverse x with y, such that when we differentiate both sides, we get 1 over 1 plus x squared. So that is the derivative of tangent inverse function. And on the right hand side, we have dy over dx. And when we rearrange the equation, we get dx over 1 plus x squared is equals to dy. Now we're going to replace this value in our integral, the original integral. So that should give us integration of y dy. So we've replaced tan inverse x with y and dx over 1 plus x squared with dy. Now this is a very simple integral. So using the power rule, we know that integration of y dy gives us half y squared plus c. Then finally we're going to replace y with its original value. So that's tan inverse x. So we get half of tan inverse x whole squared plus c. Example number 2. So here we have integral x squared times e raised to the power of x cubed dx. So by using the method of substitution, we are going to substitute x cubed with t, and then we are going to differentiate both sides with respect to x. So that should give us thrice x squared dx is equals to dt. Now we consider the integral, then we're going to rearrange the terms. So that should give us e raised to the power of x cubed times x squared dx. Now what we're going to do, we're going to multiply and divide the integral by 3. So this will help us to replace e raised to the power of x cube as e raised to the power of t, and x squared dx times 3 will be simply dt, and integrating that should give us 1/3 e raised to the power of t plus c, and finally we're going to replace t with x cube, so we get 1/3 of e raised to the power of x cube plus c. So here in problem number 3 we have the integration of e raised to the power of x divided by 1 minus e raised to the power of x dx. So let us substitute the denominator 1 minus e raised to the power of x with t, and differentiating both sides gives us negative e raised to the power of x dx is equals to dt. And integration of dt over t is going to give us the natural log of t, so that gives us finally negative log of t plus c, and replacing t with 1 minus e raised to the power of x, so we have negative log 1 minus e raised to the power of x plus c. Number 2. Integration by parts. Integral of the product of two functions is equals to first function times integral of the second function minus integration of the derivative of the first function times integral of the second function. Let's do a problem. So here we have integration of x squared times e raised to the power of dx. So we're going to treat x squared as the first function and e raised to the power of x as the second function. So here we have x squared times integration of the second function, that is e raised to the power of x, minus integration of derivative of the first function, that is derivative of x squared, multiplied to derivative of e raised to the power of x, and then we integrate it with respect to x. So that should finally give us x squared times e raised to the power of x minus integration, so derivative of x squared will be twice x, times integration of e raised to the power of x will be e raised to the power of x dx. Now what we have, we again have integration by parts, so we have to integrate into the second term, which is integration of x times e raised to the power of dx. So following the same method, that should finally give us x e raised to the power of x minus e raised to the power of x plus c. Problem number 2. So we have to integrate the logarithmic function. Now here we have only one single function, but what we can do is we can rewrite it as the product of 1 and log of x, such that we can treat the logarithmic function as the first function and 1 as the second function. So we have log of x multiplied to integration of 1 dx minus integration of derivative of log of x times integration of 1 dx, and we integrate it with respect to x. So that should give us log of x times integration of dx will be x minus the derivative of log x is 1 over x and integration of dx is x dx. So you can clearly see that the x and x gets factored out, so that leaves it behind on the integration of dx, and that should finally give us x log x minus integration of dx, which is x plus c. Number 3. Integration by partial fractions. Let's understand this particular concept with the help of a problem. So here we have integration of 2x squared minus 1 over x times 1 minus x squared dx. So we are going to use the method of partial fractions. So let us suppose that 2x squared minus 1 divided by x times 1 minus x squared, where the denominator 1 minus x squared can be factored as the product of 1 minus x times 1 plus x. And we're going to rewrite it as equals to the constant a over x plus b over 1 minus x plus c over 1 plus x. What we have done is we have divided the given fraction into partial forms. Now we're going to multiply both sides by the denominator of the term on the left hand side, that is x times 1 minus x squared. So that should give us 2x squared minus 1 is equals to 1 minus x squared times a plus x times 1 plus x times b plus x times 1 minus x times c. Now what we have to do is now we will try to find out the value of a, b and c. To do that, we are going to substitute the value of x with 0 to get a equals to -1. We're going to substitute x with 1 to get b equals to half, and x with -1 to get c is equals to -half. So that gives us 2x squared minus 1 over x times 1 minus x squared in the form of partial fractions. We have -1 over x plus half over 1 minus x plus -half over 1 plus x. Now we're going to integrate both sides with respect to x. So that should give us negative integral dx over x plus half times the integration of dx over 1 minus x and minus half times integration of dx over 1 plus x. So integration of dx over x is the natural log of x. So we have negative log of x minus natural log of 1 minus x minus half times the natural log of 1 plus x minus the natural log of c. Now in the second term we have a negative sign, we have negative log. So the negative sign is coming, which we can find out by using the method of substitution. Now what we have, we're going to use the property of logarithms. That is going to give us negative times the natural log of c times x times 1 minus x times 1 plus x. We can combine 1 minus x times 1 plus x to get 1 minus x squared. So the final result will be negative log of cx times 1 minus x squared. 1.4 Logarithmic and exponential formulae. If x is greater than 0 and y is greater than 0, then number 1, log of x plus log of y is equals to log of x times y. Number 2, the difference in log values, that is log of x minus log of y, is equals to log of x over y. Number 3, n times log of x, where n is any number, any rational number, so that is equals to log of x raised to the power of n. Number 4, y is equals to natural log of x, so that is also equivalent to x is equals to e raised to the power of y. Number 5, the logarithm of 1 is always 0 and natural log of e is equals to 1. Number 6, e raised to the power of x multiplied to e raised to the power of y is equals to e raised to the power of x plus y. And e raised to the power of x divided by e raised to the power of y is equals to e raised to the power of x minus y. Number 7, e raised to the power of natural log of x is equals to x. Let's do a few numericals to understand the properties of logarithms. So here we have question number 1. Express y in terms of x. So we have log of y plus 3 minus 2 times log of x is equals to x. So what we're going to do, we're going to rewrite this equation as log of y plus 3 plus within brackets minus 2 multiplied to log of x is equals to x. We have log of y plus 3 plus log of x raised to the power of negative 2 is equals to x. Now we're going to use the product rule. So before using the product rule, so we're going to rewrite the second term. So we have log of y plus 3 plus log of 1 over x squared is equals to x bigger. And then we are going to combine now using the product rule. So we have log of y plus 3 multiplied to 1 over x squared, and that is equals to x. And finally we have y plus 3 over x squared is equals to e raised to the power of x. Now we're going to rearrange since we have to write in terms of y, so that should give us y is equals to x squared times e raised to the power of x minus 3. Problem number 2. So here we have to simplify 3 times log of x plus 2 minus 2 times log of y minus half times log of twice x plus 3 is equals to log of c. So let's rewrite it. So we'll have log of x plus 2 raised to the power of 3 plus log of y raised to the power of negative 2 plus log of 2x plus 3 raised to the power of negative half, and these are all equals to log of c. So we have log of x plus 2 raised to the power of 3 plus log of 1 over y squared plus log of 1 over square root of 2x plus 3, that is equals to log of c. Now we're going to combine the 3 terms on the left hand side. So that should give us log of x plus 2 whole cube divided by y squared times square root of 2x plus 3, that is equals to log of c. Now we can get rid of the log from both of the sides, so that should give us x plus 2 whole cubed divided by y squared times square root of 2x plus 3 is equals to c. Or we can simply rewrite it as x plus 2 whole cubed is equals to c times y squared times square root of 2x plus 3. 1.5 Partial derivatives. Let z is equals to f of x and y be a function of two variables. we recall that partial of z with respect to x and partial of z with respect to y are the first order partial derivatives where number 1, partial of z with respect to x is obtained by differentiating z with respect to x treating y as constant. Number 2, partial of z with respect to y is obtained by differentiating z with respect to y treating x as constant. Problem number 1. If m is equals to x raised to the power of 4 minus 2xy squared plus y raised to the power of 4, then we need to determine the partial of m with respect to x and partial of m with respect to y. So we begin by finding the partial with respect to x. So we rewrite the equation as m is equals to x raised to the power of 4 minus 2xy squared plus y raised to the power of 4. So we take the partial of each of the terms with respect to x. So we have partial of x raised to the power of 4 with respect to x minus partial of 2xy squared with respect to x and partial of y raised to the power of 4 with respect to x. In the first term, we can rewrite it as d dx of x raised to the power of 4 minus 2y squared, that being a constant we have pulled it out, times d dx of x plus y raised to the power of 4 is again pulled out, it being a constant, we have d dx of 1. So you have 4x cubed minus 2y squared times partial of derivative of x with respect to x is 1 plus the third term is going to be 0. So finally we get 4x cubed minus 2y squared. So now we are going to partially differentiate m with respect to y. So we consider the function m and we're going to partial of x raised to the power of 4 with respect to y minus partial of 2xy squared with respect to y plus partial of y raised to the power of 4 with respect to y. So the first term we can pull out x raised to the power of 4, so that being a constant. So we have x raised to the power of 4 times d dy of 1 minus 2x that is pulled out times d dy or the differentiation of y squared with respect to y plus differentiation of y raised to the power of 4 with respect to y. The first term is going to be 0 because differentiation of a constant is 0. The second term we have negative 2x times differentiation of y squared with respect to y is twice of y plus differentiation of y raised to the power of 4 in the third term with respect to y gives 4y cubed. We rearrange it and that should give us 4y cubed minus 4xy. Problem number 2. So here we have a function m which is given by y times 1 plus 1 over x times cosine of y. So we need to determine partial of m with respect to x and partial of m with respect to y. So we consider the function m is equals to y times 1 plus 1 over x times cosine of y and find the partial of m with respect to x. So we're going to differentiate the term on the right hand side with respect to x partially. So that should give us partial of y times 1 plus 1 over x times cosine of y partially differentiated with respect to x. Now, since we are differentiating with respect to x, so y times cosine of y being a constant is taken out, so that is multiplied to the derivative of 1 plus 1 over x. So we have y times cosine of y times d dx of 1 will be 0 and d dx of 1 over x is negative 1 over x squared. So finally that gives us negative y over x squared times cosine of y. Now we're going to differentiate m with respect to y. So we have partial of m with respect to y. So that is going to give us partial of y plus 1 over x times cosine of y. So that will be partially differentiated with respect to y. Now 1 plus 1 over x being a constant, we'll take it out and then we multiply it to the derivative of y times cosine of y. So that should give us 1 plus 1 over x. Now we are going to use the product rule. So we have negative y times sine y plus cosine of y. So this is the partial derivative of m with respect to y. We can rearrange the terms, so that should give us cosine of y minus y sine y multiplied to 1 plus 1 over x. 1.6 Differential. Definition. Suppose z is equals to fx comma y be a function of two variables, then the differential of z denoted by dz is equals to partial of z with respect to x times dx plus partial of z with respect to y times dy. Similarly, if phi is equals to z xyz as a function of three variables x, y and z, Then the differential of phi, denoted by d phi, is defined as d phi is equals to partial of phi with respect to x times dx plus partial of phi with respect to y times dy plus partial of phi with respect to z times dz. 1.7. Some formulas on differentials. Number 1. The differential of xy is equals to x dy plus y dx. Number 2. The differential x over y is defined as y dx minus x dy over y squared. Proof. Number 1. Let xy is equals to z such that partial of z with respect to x is given by partial of xy with respect to x, so that should give us y. Since y is a constant, we pulled it out, and differentiation of x with respect to x will be 1. Similarly, partial of z with respect to y will be equals to x, such that now we use the definition, so we have the differential dz will be equals to partial of z with respect to x times dx plus partial of z with respect to y times dy. Instead of z, we're going to replace it with xy, so we have differential xy, so that will be equals to partial of z with respect to x, so that is y, so we have y times dx plus partial of z with respect to y, so that is x, so that gives us x times dy. Proof of 2. So here we are going to suppose that x over y is equals to z, such that partial of z with respect to x gives us 1 over y, and partial of z with respect to y gives us negative x over y squared. Now we know that d of z, that is the differential dz, is equals to partial of z with respect to x times dx plus partial of z with respect to y times dy, such that d of x over y will be equals to, so replacing the value of partial of z with respect to x and y, so that gives us 1 over y times dx plus negative x over y squared times dy, and when we rearrange it, so that should give us y dx minus x dy divided by y squared. 1.8. Differential equation and its order and degree. An equation containing derivatives are referred to as differential equation. Some examples include dy over dx plus 3xy plus x squared. Number 2. The second derivative of y with respect to x plus the first derivative of y with respect to x plus y is equals to 0. Number 3. The first derivative of y with respect to x whole squared plus 2 times the first derivative of y with respect to x plus y is equals to 0. And number 4. The third derivative of y with respect to x whole squared plus the first derivative of y with respect to x whole cubed plus y is equals to 0. The order of the highest derivative appearing in a differential equation. The power or exponent of the highest order derivative gives the degree. So in the first problem, the order is going to be 1 because we have a first order differential involved here, and the power or the exponent of the first order is 1, so degree is going to be 1. In the second problem, we have a second order differential equation and the power of the second order differential is 1, so the degree is going to be 1. In equation number 3, the highest order is a first order, so we have a first order differential equation of 1 and the power or the exponent of the highest order is 2, so the degree is going to be 2. And finally in number 4, the order is going to be 3 and the degree is going to be 2.